Okay, so a reminder, tonight we have an exam. I will be around, but you know your room assignments, I think, by now. Same as last time. All right, so today we're going to continue with the material on extremizing functions and talk about Lagrange multipliers. Before I get there, I wanted to do one more problem related to extremizing over a bounded domain. I think last time we sort of rushed at the end. So let me do one more problem. Reviewing. And while this material won't be on the exam, there are some things that we'll do here which certainly are related to things we've learned that will be on the exam. So let's suppose we have a function f of xy equaling xy minus x minus y plus 1. And this will be on the domain D in the plane, which is going to be described as follows. We're going to take the x coordinate has to be non-negative, y coordinate non-negative, and sum of x plus y should be less than or equal to 4. So it's not true in general that if you just throw out some random inequalities that you're going to necessarily get a closed and bounded domain, but in this case you do, and we'll take a look at what this is in a moment. So knowing that it's closed and bounded tells us there will be an answer to the following question. So find the absolute. So absolute is another word for global. Think of this as global. Global. Min and max of the function f on D. Okay, so let's remember what our technique here was for solving this. So the first thing we do is we try to solve the local problem. And we do that on the interior of D. But before we get started on that, it might be helpful to see what is D. What is the picture of this domain? Well, if we look at the first two inequalities, this is just saying that x and y have non-negative coordinates. And that set of such xy forms the first quadrant. So here, if we want to sketch D, we can sketch it in the xy plane by saying, okay, well, the first two inequalities give us everything in the first quadrant. And now, in general, what is helpful if you want to then find the remaining inequality, what it tells you is to go to the boundary of that inequality by looking at the equality, right? So if we replace this inequality with an equality, that's right where we're just going to cross the threshold of the bound. So that's x plus y equaling 4, and that's a line of slope -1 with y-intercept 4. So we get this line here, something like this, and it's going through these points, 4, 0, 0, 4. And everything on the left-hand side, sort of over here, is going to satisfy this inequality, less than or equal to 4. So we can take the intersection of these two sets, everything on this side, and then all the things in the first quadrant, and we'll get our domain D. So that gives us this domain. That's our D. Label my axes. All right. So once we have a picture of this in front of us, I think it is helpful to sort of see which points are where. So now, let's go ahead and try to solve that local problem. And we don't really need the picture to find critical points. We can just go ahead and take the gradient of f and set it equal to 0. So first we'll calculate the gradient. We take the partial of f with respect to x, that gives us y minus 1. The partial of f with respect to y gives us x minus 1. And we want to set this equal to 0 to find critical points. So it's pretty clear the only solution, we have to solve both of these equations simultaneously. The only solution is that xy is equal to 1, 1. Not a hard example here. But now, again, this is where it's helpful a little bit to get the picture. You want this point to be inside of this region. Now you can do one thing, you can look at the picture and say, okay, well, it's right here, so I know it's in there. Or you can say, well, does this point satisfy these three inequalities? And well, since 2 is less than or equal to 4, sure, it does. So this is D. All right, so now it's nice to just apply a second derivative test and see what type of critical point this is, what the local behavior of f is near this point. So here we can just calculate the Hessian. And in this case, we have to take the partial of y minus 1 with respect to x, that's 0. Partial of the mixed partial is going to be 1. We'll get a 1 here, and we'll get a 0. These are this matrix of second partials. So the discriminant, which is the determinant of this Hessian, is just 0 minus 1. So this equals negative 1, which is less than 0. So if it's less than 0, we know by the second derivative test that this point is a saddle point. So if we're trying to find absolute or global min max, this is not going to be it. And we're really just going to be on the boundary to find these global min maxes. So we need to check the boundary. Now, to check the boundary of this case, we need to actually check 3 different possibilities, because we really have 3 different kind of sides to this triangle. And each side, we need to extremize this function restricted to that side. So let's do that. So I'll just redraw this triangle. So I've got the origin here. I've got the point 0, 4 here. And I've got the point 4, 0 here. And using the technique we had last week, we need to parametrize this boundary. But as I said, it's kind of not pleasant to parametrize it all at once. Just parametrize each side. So let's label this side A, B, and C. You'll see A and B are pretty close. We can get a simple parameter. So how do we parametrize this side A? Well, we see that the x-coordinate is staying at 0 for the whole thing, right? And t is varying, or y is varying from 0 to 4. So we can just give a parametrization r of t equaling 0 t, 0 to 4. That will parametrize that side. And then we stick this parametrization into our function. So f of r of t, this is case A. F of r of t, well, I need to look up a little bit and see what f is. It's this function up here. So I just put 0 in for x and t in for y. And so I'll get 0 minus 0 minus t plus 1. So this is a function of one variable on the interval 0 to 4. So I can look at this graph of this function in terms of t, 0, 4, right? And it's going to be, it's going to look like this. It's going to be a line like this. That's the graph. Where this is height 1 here and height 3 here. I'm sorry, negative 3. Ooh, I'm sorry. Yeah, negative 3. So what are we trying to do on this edge? We're trying to extremize this function, trying to find the maximum values of f along this edge. Well, you can see that the largest value of f along this edge is 1, and the smallest value, or the smallest value, is negative 3. So f of, well, maybe we'll say candidates for the extreme values here are 0, 0, which is sent to 1, and 0, 4, which is sent to minus 3. Of course, these are candidates for the extreme values, but not the same type of extreme value, not the min, as we'll find at the end. All right, what about B? So this is it for A. Now we want to parametrize this edge, but we can do the same exact type of thing here. So we can just take, instead of the y coordinate going from 0 to 4, we can take the x coordinate. Oops, sorry. Going from 0 to 4. And as you'll see, if you do that, you get precisely the same function, because there's a symmetry for this function in terms of x and y. I'm going to, since I'm losing touch with my function, I'm going to bring it down here. Let's put it here. So if I put f of r of t in this case, I'll get precisely the same function. I get minus t plus 1. So the points of interest here, candidates, as I called them before, 0, 0 is still going to 1, and 4, 0 is going to negative 3. So now if I sort of look at all of my candidates on the shape, I've got just the endpoints here, the vertices of this triangle so far. So now I have to do the last edge. It's part C. And for C, this is precisely where x plus y equals 4. So here we have x plus y equals 4. And you can choose your coordinate, either one, or y is equal to 4 minus x. And you can parametrize this. Here x goes from 0 to 4. You can parametrize this just with this equation. So take r of t just equaling t 4 minus t. Here you're taking t for x, and then you have this equation y equals 4 minus x, so you take 4 minus t for y. And we're bound for the x variable. You can see this x variable is bound between 0 and 4 here. So that's where our t is going to range. Now we put this in, just like we did with these other two cases, to f. And we're going to get something a little less pleasant, but not too bad. T times 4 minus t minus t minus 4 minus t plus 1. We'll get a little simplification. So we'll get 4t minus t squared. The negative t cancels with plus t, so I'll get a minus 4 plus 1 is minus 3. Which is equal to negative t squared minus 4t plus 3, which equals minus, I guess, t minus 3, t minus 4, t minus 1, pardon. Great. But, well, this, I don't know if this is necessary. Doesn't give us the roots, but I'm not sure. Do I need that? I don't, probably not. Because what I really am after is I'm not really after, well, in some ways you can see something from that, but maybe what I'm really after here is the critical point. So because we've already done these two paths and we've already analyzed these two endpoints, we're really only interested in what's happening inside of this last side. So we're really just going to look to see if f has any critical points there. So let's calculate the derivative of this, d dt of f of rt. And I'll use this, this formula here. It's the easiest, seems. I'll get 4 minus 2t. This is equal to 0. I want to find critical points here. So I'm going to set the derivative equal to 0. And so I'll get t is equal to 2. Now when t is equal to 2, we get r of t is equal to 2, 2. 2, 4 minus 2 is 2. So this is the last point of interest that we want to explore. And we'll take f and we'll try to analyze. This is our last candidate. We'll analyze, or just calculate, I should say, what the value of f is. So each of these little squiggly arrows, I'm just taking the value of f at these points. So here, let's do it again and take f at that point. Sadly, I've lost my f. Bring it down more. So here, I can analyze this, f of 2, 2. Just calculate this, I should say. 4 minus 2 minus 2 plus 1, which is 1. So we have all of the possible candidates, and we can see that indeed the minimum, or absolute minimum, is 1. Sorry, is negative 3. Is negative 3. And the absolute maximum is 1. And it does pay in applications to know where these are achieved. So this is achieved here at 2 points. So if you're asked in a problem on an exam, find the absolute maximum, find the maximum value of a function, you go ahead and give the maximum values and minimums. If you're asked where these are achieved, then you have to actually tell me where these are achieved, or tell whoever is asking. And so this, it's not achieved at 0, 0, 0, 4, 0. Whereas it achieves the value of 1 at 0, 0, and 2, 2. So it's achieved twice in both cases. Okay, so this is how you have to do these types of problems. And honestly, this is sort of the best way to do this type of a problem, I would say, if you have something like a triangle. However, last class we had a disk, and with a disk it's a different story. With a disk, we're looking on something that is described, the boundary was described by a single equation rather sort of than 3 equations. And so there's another method that we can use, which is Lagrange multipliers. So oftentimes, I'll say often, the boundary of your domain is equal to a single constraint. So it's equal to the set of points satisfying a single constraint. And where g is a nice function, so where g is nice, and what that means is, when I say nice, is that the gradient of g is non-zero for all solutions to this equation. That means that you have a kind of a smooth curve. It's not singular. So not like the triangle where you have these corners. Now, when you have this is called a constraint. It's called a constraint. And you know, we have other vocabulary that we use for this, which is to say this is a level curve of the function g itself. So we have a level curve. And now this is all done when we're talking about a constraint or a domain whose boundary is a constraint. This is all done in this context with a background function f that we're trying to extremize. So we have some function f that's sending our domain to real numbers, and we're interested in the values of f and the points where we achieve critical points of f. And now here comes a very tricky and delicate thing, which is if we just look at f on the boundary, we will get some critical points. But if we looked at f on the domain B itself, those points will not be critical. So restricting f to a constrained space, a curve, for example, makes certain things critical that weren't critical in the larger space. And I'm going to give you a picture to really hopefully convince you of that fact. So let me move over to the figures here and copy this up. Okay. So let's consider this function. So our background function will be f of xy equaling x squared plus y. Now I'm going to give you a constraint. Well, our domain, not so important here. It's just maybe all of R. Maybe we're not thinking of the boundary. We're just thinking of, maybe you could take the domain to be the pot y is greater than or equal to 0. So let's do that actually, just to keep in the context of what I'm talking about. So if this is the domain, which is just this region here, then the boundary of the domain will be this x-axis, will be the x-axis. So let's take this guy and we'll style this. And it's given by this simple constraint, a very simple constraint, y equals 0. So we can take this, just the function y, to be our constraint. Now, when we look at the graph of this function, right? We look at the graph of this function. Take this is a drawing of the graph, and we'll just put it over the space. We've got our z, this is our height. This is f of x. Sorry, this is z, and this is the graph z equals f. Now you can see, just by a basic computation, if I take delta of f, or nabla of f, excuse me, that I will get 2x, 1. This is never 0, because the y component is 1, always. So we're never going to get 0. There are no critical points. And indeed, I don't have any maxima or minima. I'm always kind of able to go up or down. No critical points of this function f on the whole space. However, when we restrict to our constraint, and we just look at the graph over that constraint, we get the function x squared over the line. That does have a critical point at the origin. So over this constraint, boundary of D, f has a critical point. So f it's just x0, which equals x squared. So here, what I need to use the language very carefully. I need to say this point that I'm interested in, this particular point here, namely the origin, is a critical point of f restricted to the constraint, restricted to the boundary of D, or restricted to y equaling 0. It's not a critical point of f on the whole space, just when I restrict it to this constraint. Is that clear? It's very subtle. I think it's a very subtle point, but okay. Point is when you're trying to maximize on these regions, if I'm just maximizing on this positive part, these are the points that I'm going to be interested in looking at, these sorts of critical points. Maybe if I could have, you can see this as sort of this doesn't appear as a maximum, but if I had done it on this side, actually this would appear as a minimum of the function. So what we're going to be interested in, and what we were certainly interested in up here when we calculated the constraint here, is we found this critical point on that edge, which again is also not a critical point of f, but it's a critical point when you restrict f to that edge. So that's what we're interested in finding, and that is precisely what Lagrange multipliers help us identify. They help us find those points. Okay, so let's talk about Lagrange multipliers. So this gives a method for calculating critical points, or at least finding them in good cases, of a function f. And this can be in this Lagrange multipliers works in arbitrary dimensions, but we are going to focus on 2 dimensions today. Of a function f of xy restricted to a constraint. So the set of xy satisfying an implicit equation g of xy and 0. In other words, we're on a level curve of g. Okay. So let's see if we can. I'm not going to prove that the equation is what it is, but I do want to give you a sense as to why you should expect this equation to tell you the answer to this question. So what I'm going to do is draw a picture. Better picture. So here's our xy plane, Cartesian plane. And let me give myself a curve. And I don't know if this curve will be something like this. This is g of xy equaling 0. So I'm not interested in f on the entire plane. I'm interested in f on this blue curve in the plane. But f is defined as a function of x and y. So it's defined at least in some region around this blue curve. It doesn't have to be defined everywhere on the plane. So I want to see when, let's say, f is maximized or minimized when I just look at f restricted to the blue curve. So to do that, one way of thinking about that is to sort of draw the contours of f. Draw the contours of f. So let's say f has some contours that look like, this. This will be a contour of f of xy, I don't know, equaling 0 itself. And we kind of we draw the other contours of f. So this contour, this is f of xy equaling 1, and maybe we have some other ones going here. So I draw the contours of f. Now, if I think of the contours of f, and I think of what's happening here, if I'm on the f equaling 0 contour, and I kind of can go up to the f equaling 1, then I should be seeing f increasing as I go from here to here, that direction, and f decreasing as I go here to here. So if I stay on the blue curve, I'm going to be increasing when I look at those contours. The only time I'm going to not be able to sort of increase on the blue curve is when I get to that contour of f that is tangent, precisely tangent to the contour of g. to the levels, to the constraint G equals 0. Right here, I don't have any possibility to increase F, right? I've increased it this way, and if I keep on going on the curve, I'm going to be decreasing, going back to that contour 0. So it's right when these two curves are tangent, just touching each other, that we're going to get a local max or a local min. But how do we express that formulaically? How do we say these two curves are tangent to each other? Well, we remember what our gradient tells us, the kind of information our gradient tells us. One of the things the gradient is it's normal to the tangent line of your level curve. So if I look at the gradient of F, I get a gradient going like this at that point. This is the gradient of F. And if I look at the gradient of G, and this depends on the direction, it's also going to be normal to the same tangent line because they're tangent to each other. So maybe it's pointing the opposite direction, I don't know, but it's pointing in that same, it's a multiple of the gradient of F. So now the question becomes, well, if I'm looking for these points, I'm looking for those points where the gradient of F is a multiple of the gradient of G. And that is precisely this Lagrange equation. So we want to solve this equation. Find those points on G equaling 0 for which we have a solution to this equation. For some lambda, some real lambda, some scalar. So this is a theorem. We just summarize this in this theorem, main theorem here in this section of the book. So suppose C, which C stands for curve, although again, this is something you can do in any dimension, is given by a constraint G of xy equaling 0, where here we really do need to make this assumption that the gradient G is always non-zero on C. And of course, the 0 on the right-hand side there is a 0 vector. And we'll also assume that f of xy is differentiable on D, or sorry, on C. So then the critical points of F restricted to C are points A, B, for which there's a solution to the equation that I just wrote about. Oops. B is equal to lambda gradient of G at AB for some real number lambda. And lambda can be 0. If lambda is 0, then F is critical at that point on the larger space too. All right. Let's look at an example that we just saw a second ago. So sort of the baby example. Before we had this function G of xy equaling y. This is that red line, red curve that we drew. just the x-axis, y equaling 0. This describes. And then our function that we f of x, y, this was equal to y plus x squared. So we calculated the gradient of f. This is just 2x, 1. And we can calculate the gradient of g, which is just the constant vector, 0, 1. So what we're looking for is, if we're trying to solve this equation, which we are, is we want to see if there is a solution. So we want a solution to the equation 2x, 1 equals lambda times 0, 1, or just 0 lambda. Well, if I have a solution to this, then I know two things. So I'll need that lambda is 1 and x is 0. But we don't, and this is a part that oftentimes people forget about or miss, is that we don't want any solution. So our solutions to this equation is not the entire y-axis. We're looking for solutions to this equation that sit on our constrained space. So we want a solution that also satisfies this constraint. Well, that just means y has to be 0 too. Due to the constraint. G. So the only point here is the origin. Okay. So this may be like some kind of thing you're just like, what's the point? We got a lambda now, so why do we need extra stuff? So one thing I hope that all of you will have noticed or if you haven't, it's okay. You can notice it now. In the formulation of this, we have this equation g equaling 0, right? And we look down, how do we find the critical points? We're taking a gradient of f and a gradient of g. And we're trying to solve some equations there. What did we not have to do? What did we not have to do? Which you should be really happy about. What did we do before last class and earlier, a moment ago? Yeah. Okay, that's true. Okay, so the statement is a statement about the second derivative test. Now, what Lagrange multipliers is going to give you is it's going to give you critical points. It is not going to tell you necessarily the local behavior of those critical points. So you still may need to do some kind of analysis. This is just getting the critical points on a constrained space. So that's something you still might have to do in general, but in the case where you just have a one-dimensional curve, it's not going to be too hard. You can just compare values if you're looking for global extreme. I want to say something that is I believe in you guys. I think that you can do that part. But I don't believe in you guys enough to believe that if I give you a random equation for g, a random function g, that you'll be able to take that level curve and parametrize it. Because it's very hard to do. It may be impossible to do. But what Lagrange multipliers does not require is for you to parametrize. You do not need to parametrize. You just solve this equation of the gradients, which is often easy to calculate. So this is a really powerful tool to kind of get around having to parametrize curves or surfaces in higher dimensions. Very, very powerful. That's why you'll see it in a lot of applications. All right, so let's do one more problem, and let's look at the problem we did last time, where we did parametrize. So last time we had the following question. So find the global max and min of the following function. It's f of xy equal to x squared minus x plus y squared on the disk and call it d just for notation's sake. X squared plus y squared is less than or equal to 4. So let's see. What did we do last time? Well, last time we calculated the gradient, which we'll still need to do, but it's a very easy calculation. And we found that f, this is last time, just to remind us, found that f has a local min at the point 1/2, 0. Okay, we parametrized this boundary, which is a circle. And so in this case, it's not too hard. But again, if I give you a more difficult region, it may be quite hard. Boundary of D. And we found that we had 2 points, which I don't think we actually wrote this out, but it was 2, 0, which is the point R of 0, and minus 2, 0, where the values of f were 2 and 6. Oops, minus 2, 0. And then we were able to look and compare values. I'm not sure we calculated the value of, did we calculate this? We probably did. I don't remember. I think this goes to negative 1/2, negative 1/4. So we could calculate, we could compare these 4 values and get that 6 was the maximum, and negative 1/4 was the minimum. Okay, but what you don't want to have to do is this step where we parametrize the boundary. That can give you headaches in general situations. So rather, let's use Lagrange multipliers and see that we get the same 2 points. So what we're going to hope for is that we get these 2 points as our critical points of f on the boundary. So let's find this without parametrization. Using Lagrange multipliers. Okay. Now, I will make a comment. These multipliers are not really the main thing in this technique. This lambda, which is the multiplier, is not that important. It's more that it helps you get these critical points. Okay, so what is our constraint? We need our function g. Well, this boundary is where we're looking at the constraint. And the boundary is precisely when we take this inequality and make it equality. So the constraint here is just x squared plus y squared equals 4. And if you want to write that as an equation g equaling 0, you can take g of xy to equal x squared plus y squared minus 4. Okay, now we're going to calculate, we want to solve this Lagrange equation. So we're going to calculate gradient of g. And that's not hard. You just get 2x and 2y. So the equation that we're interested in solving, the Lagrange equation here, the Lagrange multiplier equation. There's another Lagrange equation in classical mechanics, which is different. So anyway, is setting the gradient of f, which we calculated above, 2x minus 1, 2y, this is the gradient of f, equal to lambda for some lambda times the gradient of g, which is just going to be 2 lambda x, 2 lambda y. So this is the equation we want to solve. So let's be clear about what we want. We want to find all xy for which two things happen. A, lambda exists in solving this equation. And B, g of xy is 0. We want to be on that constrained space. We do not want to solve star this main equation for all the points in the plane. That's not our interest. We don't care. We're just interested in this circle in this case, or the constrained space in general. Okay, so let's take a look at A. Well, this vector equation here is really two equations, right? So we have 2x minus 1 equals 2 lambda x, and we have 2y is equal to 2 lambda y. It's a very nonlinear equation, so you have to be a little bit careful. In particular, what many people will be tempted to do, which you don't want to do, is they'll say, oh, this equation means lambda is 1. Right? However, you don't want to do that, because that equation does not mean lambda is 1. Right? If y is non-zero, then lambda is 1. However, y can be 0. So you need to take a couple of cases. So let's start with our good instinct and say, if y is non-zero, then, well, lambda must equal 1 by the second equation. I mean, just divide by y. But then 2x minus 1 equals 2 times 1 times x, which is 2x, or negative 1 equals 0. And the universe explodes. This doesn't happen. Negative 1 is not 0. So this is not going to give us any solutions. So we don't want this case. That case leads to no solutions. So thus, y must equal 0. And then x can be whatever is possible. First equation will have a solution, and I don't really care. The only time the first equation may not have a solution is if x is 0, but both y and x can't be 0 because of part B. Then let lambda be whatever, be anything it needs to be. In other words, what I'm trying to say is that the first equation will have a solution. This is because x is non-zero. But now we can say, okay, let's look at B. We want that g of x, which as you'll recall is x squared minus y squared minus 4 to equal 0. If y is 0, that means that x squared equals 4. So for y equaling 0, which means that x is plus or minus 2. So thus, our two critical points on the circle are precisely plus or minus -2, 0, and 2, 0. Now, again, I want to reinforce what I said. When you look at these steps I'm taking with A and B and with solving this equation, there is no cosine or sine. I did no parametrization of this boundary. It's just solving some basic equations. So this is very helpful. All right, guys, good luck on your exam tonight. I will see you tonight or Tuesday.